So remember the first slide up there. What is truth? That's the question here, isn't it? You know, you can work, we were talking during the break, 1 mile project, you know, you got a small job, and you can make that work relatively using GPS, you know, because everything works pretty well together. We said we could use just ellipsoid heights if you can hold an elevation on something, have something to check maybe, so you know the relative difference between them works. But of course the question is, well, we take that job and you take your job over here and you take your job over here, do they fit together? And the GIS people want them to fit together, of course, but what is acceptable? You know, and I heard 2/10 from job to job is typical. A lot of areas in New Orleans, you do some work and somebody else does some work and you check their elevations and orthometric heights, 2/10 of a foot. So, and I'll just repeat it, you guys are between a rock and a hard place here. And that's the most important question. What is the truth to you? It's not what you use, it's what you're going to hold. That's the most important question. And I don't think there is an answer. Another thing to remember is, like I was telling you about state plane coordinates. Do we typically use state plane coordinates on plats here? I mean, or do we use coordinates on plats here? Yes? Yeah. Okay, so in Maryland we do too. In Baltimore County it's required to have NAT 83, I'm not sure they specified the adjustment, but NAT 83 coordinates on plats. And I'm telling you what's being done. People go out and they'll GPS some control points, and those control points will be 1,500 feet apart. You know, and they'll set up a total station and they'll read between them, and it'll check, you know, a few hundredths or something. They said, okay, well, yeah, all right, you know, atmosphere and stuff. And then they'll go ahead and do their work, and they'll check in to themselves, okay, and they'll do work based on state plane coordinates on those points, and they're measuring on the ground. Okay, now in Maryland it's not a big deal, probably not a big deal here either, but in some places it's a big deal, like think of Colorado, you know. And when you go back to the office and the engineers get the data, they just plug in the values, right? And you're using all ground distances from those points that are referenced to state plane values. State plane down here, right? And the ground's up there. The distances between these 2 points are different than the distances on the ground. So the engineers will design everything. They'll design a bridge, a building, and you go back out to stake it, and you're working on state plane coordinates, and they don't check. And so it's just another thing to remember. There's also been a lot of work with single base real-time positioning where you'll set up on a monument and you take out the data sheet and you'll type in the coordinates for that monument, state plane coordinates. Okay, and then you'll say, well, you know, I know it's not a big difference here, so we won't localize to any more mines, we'll just do some work. So you go out and do work and you're getting all state plane coordinates as you go, but they're not based on the distance from the base station to where you are in the ground. So just something to remember. Not a big deal here, but just remember state plane's not on the ground, that's all. Couple ways to get around it. We don't have to really get into these, but you can actually, in Colorado, they set up low distortion projections on the ground. They put a projected surface onto the ground, and they use that. And they make sure that the coordinates don't look like state plane coordinates. They knock some digits off or something. One way. Another way is just to use a small little job, just do a tangent plane from a point on the ground, and that's another way. And a lot of the DOTs use modified state plane. They'll take a state plane value and they'll project it up to the surface, and they'll knock some digits off and just hold those as coordinates and use a ground distance between them. So it's just another way to deal with it. Something just to be aware of, just to be aware of. It's not a big deal. The thing is, like anything else, you've got a network here, GolfNet, that covers the state, goes across the state borders, and it's been very tightly adjusted, very precisely adjusted, so that everything fits together. And Randy knows when anything moves, when the antennas move, he knows that. Not true with what you use for your work on the ground. So, and they've been done at different times, with different leveling campaigns, with different height mod campaigns, with different equipment at different time, with different people. And you're finding this more and more and more and more across the country, that the real-time networks are very precise. Whether they're aligned to the National Spatial Reference System or not, internally they're very precise. The campaigns that set the marks in the ground are not. You're getting disparity. So, we are heading toward real-time networks as being, and I have a slide that reflects this, we're heading toward away from marks in the ground, and remember we said in 10 years we'll have the cores as the source of the vertical data. Well, people don't use cores for real-time positioning because we don't broadcast real-time data. So what do? They drop back to the real-time network that does broadcast real-time data. So it's important that that network is aligned to the truth. That means that you get precision and you also get truth, hopefully. So you start out, remember, you start out with WGS84 datum, XYZ coordinates in the satellites. Your data collector then sees them and converts them to a latitude, longitude, and ellipsoid height. Okay? You'll take the ellipsoid height, take lat long ellipsoid height, and then your data collector will project that datum to the grid, the state plane grid. So now you have a north, east, and ellipsoid height. Right? Then it'll take the geoid model and use it with the ellipsoid height to get an elevation, or an orthometric height. So you end up with an elevation north and east in the state plane. But you started with XYZ from the satellites. The satellites are the realization of your datum, not marks in the ground, essentially, when you use GPS, right? The other choice is to localize or calibrate to marks around your project that you trust, and the good thing about calibrating is you can see how they fit together. That's a good thing, although they could all have subsided the same. That's what happens a lot of times. But that's a good thing about a calibration. Height mod is using GPS for elevations, okay? This is the best way to do it. With NAVD88, you do geodetic differential leveling. And it's a lot of money, and a lot of time, and a lot of person power, and a lot of post-processing, but it gives you millimeters. However, if you were going to do that to the top of that rock, that would be your life work, if you wanted to geodetic level to that. Whereas you take a real-time rover and put it up there and you've got 2 centimeters, hey, that's great, because that's what you're going to get anyway when you geodetically level it. That's what your error is going to be. So that's the idea of height mod. Densify the good NAVD88 marks in the ground, benchmarks using GPS. I should say GNSS, Global Navigation Satellite Systems, including GLONASS and the rest. Hello? There we go. So, static GPS, or GNSS, is the best way to propagate coordinates and heights. It is the best way. But you've got to post-process all the data. You have to plan. You have to have, if you do a height mod project based on the guidelines, there's a lot of work involved with static. This is when you want to use static GPS, when you're doing a county. This is Fairfax County, Virginia, that I was in private sector, and I did all that stuff there. And that's static work. It's all redundancy, it's all following the guidelines. A couple of years of work to do that. But it's the best way to do it. Of course, real time, you've got an answer when you leave the field. Right or wrong, you've got an answer. And you know it worked, it's fast, you can do it with one person, right? You can live with the play in it, hopefully. You don't have to post-process. You can look at some of the results. Can't change them, but you can look at them. And then, of course, autonomous, you got your Dick Tracy watch. So heights are harder to get than horizontal. It's just endemic. in the system, right? Remember, we only have 110 degrees worth of coverage vertically, right? Because horizontally you got 360, right? Around in a circle. But vertically you've got, whoops, you don't have here, 35 degrees either way you're starting, down to the horizon. That's all the coverage you have vertically. So that's one reason they're harder to get. Another reason is, as the signal comes through the atmosphere, it affects the vertical more than the horizontal. So that's another reason. And then another reason is there's errors in all three of these components. There's errors in the leveling that gave you the value of the benchmark. There's errors in your ellipsoid heights, not mine, I don't have errors, but your ellipsoid heights. And then the errors in the geoid model. So you've got all those errors combined, and that's going to affect your height, right? Ooh, that's hard to read. Okay, so it's distorted a little bit. No big deal, but just some of the comparisons. Basically, static is going to give you the best answer when you do it and post-process it. Opus is going to be sloppier than real time. Okay, it's not going to give you as good a result for the orthometric height. Real time, single base, if you have a mark that you know is right and you trust that mark, and by golly, that's it. If you set a base station over that correctly and do real-time work from that, that's better vertical than the network, than the real-time network. The trouble is, we don't know anything about that mark. We say it's good, but we don't really know it is. Okay? Real-time networks are the bang for the buck. Vertically is the problem. Not a real problem, but it's the weak part right now. So statically speaking, there's a set of guidelines, NGS 58 and NGS 59, ellipsoid heights and orthometric height guidelines for static positioning. These guys were developed in the 90s, late 90s. Okay, Dave Zukowski, and actually when I was with Baltimore County, I contributed to it. They were fine. When you get done all this, you get 2 centimeters locally, and you get 5 centimeters to the datum. Okay? I can do that with real time, and I don't have to do any of this. But it's still good in certain ways, because you have a lot of confidence with this when you're done. And you know everything fits together in a network. Remember the network of a county? That's when you want to use this kind of stuff. You want it to be right. You want to make sure that everything fits together like that. 500 and some baselines here, and 145 stations. That's when you're going to use static GPS. I just wanted to show you these real fast. 2 things, the field requirements and the processing requirements to do the guidelines, okay, for a large project or a county. You've got to come in from the cores to local primary network stations, 5-hour sessions, 2 or 3 of them, 5-hour sessions. Then you come into secondary, then you come into your local network, and you do at least 30-minute sessions on them redundantly, spaced by 3 or 4 hours, okay? And then you have to follow, you can't have certain parameters in the field that are too high. So that's your field requirements. Of course, geodetic receivers, et cetera, et cetera. Then you got to process it. And when you process it, you can't have any ellipsoid height greater than 1.5 centimeters error, play. And that's tough, believe me. And you have to repeat each baseline, and they have to compare to 2 centimeters. If they don't, those top 2 things, if it doesn't work, you got to reobserve, which means another trip to the field. There's a lot of work here. Some of the things you can do, you can look at the data when you take it back to the office and dump it in. You can see the path of L1 and L2 on all these satellites. And you can see that the data is pretty good. Up top, down here. Now look at satellite 5. That's got some funky data there. See it? And the little line means a loss of lock in the receiver. Then you've got a little break here in L2. So you can see the data, first of all. Okay, and you can say, oh, well, you know what? I'm going to eliminate satellite 5. Well, you can do it. Just go in and say, don't use satellite 5. And you end up, after you process, these are the satellites it held. This was done by the software. And it looks pretty good. And you can go in and see the post-fit residuals. Okay, so you're looking at this guy. And most times the software does pretty good, but you can see, well, that looks, that's okay. Here's 0 and here's the spread, okay, of the solution for each epoch of data it took. Here's another one. That's a little bit higher, bouncing up and down. Here's one that drops off a little bit. Still, it's okay, but it starts off not so hot. And then this guy doesn't pick up to here. Oh, Cliff.
When you're talking about processing, you're not talking about Opus, are you?
No, this is software, manufacturer's software that you have in your office. In this case, it's TGO, Trimble Geomatics Office. Like a Geomatics Office and TopCon and all the rest of them have the same thing. And this guy looks all right. So, what you can do when you take it back to the office, first of all, you got to have somebody that can do it, right? Somebody's going to take the time to do it. You can use other baselines if you have more than 2, if it doesn't work. You can change the elevation cutoff angle. You can use, well, the guidelines say you have to use, like 10, 14 days later, go out and get the precise orbits from the satellites instead of the broadcast orbits that you used to process it originally. You can edit the data, and there's a lot of things you can do in the software to change your results, maybe hopefully improve them. You're not going to do that in real time. And then when you do that, you end up with this. What they'll do is they'll say it's a height mod station, and they'll publish the elevation to the nearest centimeter. Okay, so not millimeter, but centimeter, or 1/10 of a foot. And they'll tell you what it is. They'll say it's determined by GPS. So actually, that goes into the database, if you follow that criteria. Not a big deal to most people. Only if you're under contract to the DOT or something, then you're going to do it. But if you're blue booking, that'll go into the database. All right. So what you're doing, the theory behind this is this. You're going to have 1.5 centimeters in your ellipsoid heights. You're going to have 0.5 centimeter in your geoid model within 10 kilometers. Okay? You have to have an average of 7 kilometers to your stations. And your leveling is going to be fixed. So you're actually holding the mark in the ground is good. All right? So there's no error there because you're holding it. So the error results in the geoid model and the ellipsoid height gives you 2 centimeters locally. That's the theory. Not always easy to get. Okay. Now, real-time positioning, bang for the buck. You got a choice. You got a choice. You can set your own base station up. You can use spread spectrum radios that you can sort of line of sight, but they're pretty robust. You can use UHF radios and go 3 to 5 miles, something like that, depending on the people on the air around you. The thing about UHF and VHF is voice takes precedence over data. You're using data. So if a trucker on the interstate is on a harmonic frequency or the same frequency you are, he's going to knock you off. So that's the trouble with that. But anyway, or you can use a modem, and you can go 20 miles, as long as you can fix the integers, which I'll explain. Then your second choice is somebody's base station on a roof that they set up. Still single point positioning, one base, one rover. Or you can use a network. And the network has a lot of advantages, I'll show you, that over single base. Problem with real-time positioning is always the vertical. Talk a little bit about these guys, but this is something that everybody that takes a pole into the field should have in the back of their mind, this stuff. Not consciously all the time, but something that you should be aware of or have knowledge of or just be aware of. The thing that makes a real-time campaign successful is the person with the pole. There's nobody telling him what to do or her what to do. There's nobody recording the data but them. There's nobody behind an instrument, getting a distance to them. There's nothing but that person at the pole. It's relying on them to get the correct result. RTK, or real-time positioning, is a difference in those XYZ coordinates. It creates a vector from whatever is held to the rover. The coordinate is computed by the difference in XYZ from the base station to the rover. And there's always a base station. even in a real-time network. There's either a virtual base station or there's a physical base station that the corrections are interpolated from. There's always a base station. So real-time positioning is always differential. It's always based on a known point and an unknown point at the rover. There will be, in the future, precise point positioning, autonomous positioning to a couple centimeters. And you can get that now with maybe a day's worth of data. But nobody's going to stay there for a day to get an autonomous position that you can do in 2 seconds, right? Differentially. So, right now, this is the bang for the buck. That's where we are. A confluence of technology. The thing about real-time positioning, the autonomous GIS grade receivers use code positioning. All the satellites have different codes, the gold codes. And they send them down, they're time tagged. When they leave the satellite, receiver gets them at a certain time. Difference in time times the speed of light is a distance, right? So it's got that distance. Well, the brilliant scientists not in the military, but in the academic field, thought about this and they said, you know what? There's only 2 signals, L1 and L2. And we know what the frequency of them is. We know the wavelength. So if we knew how many wavelengths there were, then we got a distance. So how are we going to do that? Well, that's called ambiguity resolution, or fixing the integers. Because what your receiver knows is this. It knows what part of that wavelength, that fraction of a cycle that it started recording data on. It knows that. What it doesn't know is this, how many cycles are behind it. So in order to get that distance, it has to figure out how many there are. And that's an integer number of cycles from the satellite to that partial wavelength. Integer resolution, ambiguity resolution, integer fixing, they all mean the same thing. Not easy, but it does it. It's amazing. So you add those 2 together and you get a distance. Distance from this satellite, this satellite, this satellite, this satellite, multilateration. The intersection of distances gives you your point. That's real-time positioning. So, it does it for a certain epoch of time. It fixes those integers for a certain epoch of time, and you're carrying now that resolution and the difference for every epoch after that. And that's going to determine your new position. Dual frequency receivers will now enable you to do on-the-fly integer resolution. You can walk while it's figuring it out, which to me just blows my mind. I don't know how it does it, but it does it. And it'll carry that fix until what? You walk under a bridge, or something blocks the signal. Then it has to reinitialize and start over again and figure another count. But and that's called a cycle slip. Okay, we saw those little lines on the static data, cycle slips. And then sometimes it just happens, for no apparent reason. So, as I said a year ago, this is meant to scare the crawfish étouffée out of you. And this is what's going on. We have all the satellites up there, 31 of them say GPS, and at the speed of light, 1 nanosecond, 1/1000th of a second in coming down through the atmosphere translates into 30 centimeters in distance. So we need to be very, very precise in our timing, right? Additionally, thanks to Dr. Einstein, we know that special relativity and general relativity are in play here. If we did not take them into account, real-time positioning would be unusable. You'd be moving 15 kilometers a day. Special relativity has to do with speed. And because the satellites are traveling very fast, their clock appears to run slower to us. So they have to add 7 microseconds to their clocks. And because they're so high, 12,000 miles up there, they're much less affected by gravity. So their clocks appear to run faster by 45.9 microseconds. That has to be taken into account. So when you add those 2 together, special relativity and general relativity, you have to correct the GPS receiver's clocks by 38 microseconds less a day. And they are programmed into the satellite before it's launched. If you didn't do that, it wouldn't work. because remember how precise our timing has to be. So you've got a receiver set up, and you've got a satellite up there going about 8,400 miles an hour, more or less. You're on the ground going 800 miles an hour in a different direction. And here's another satellite, and here's another satellite, and here's another satellite. The receiver has to figure out the integer number of cycles from each satellite for a certain epoch of time. So it can only have one answer for all of them, of an integer number of cycles. When your data collector, and it happens real fast now, you might even know it, I don't know. But when you first turn it on, it'll say float. Have you ever seen that? And it'll say, 2 feet or something like that. And it'll get a little bit better, a little bit better, a little bit better, and all of a sudden it'll go fixed. And it'll snap down to a centimeter or something like that. That means it got the answer. What float means is it got a decimal of the answer. It has 20,153,923.821 cycles. Well, it has to be an integer number. And it hasn't figured out whether to round it up or down. That's float. When it's fixed, it means it solved it. Right or wrong, it solved it. Now the manufacturers say 99.9% confidence in their ambiguity resolution. That's probably true, but I have seen bad integer resolution. So you have to be aware of that. That's why you always check a point. Okay? So it says, well, I could be any one of these black dots. I could have this amount of cycles for that one and this one, or it could be this one. And so it has to go through a least squares adjustment. It has error. It can resolve the problems with the ionosphere. It does differencing. There's a lot of techniques it goes through, Kalman filtering. To complicate it further, the signal coming through the atmosphere is affected by Doppler. That means that if it's coming to you, just like a train, right? Doppler, right? The sound frequency is changing to your ears. So as the satellite's coming to you, the signal's compressed, and then as it goes by you, it's elongated. So the receiver has generated its own wavelength, 1575.42 for L1. Million cycles, and but the frequency coming in from the satellite has a different wavelength because of Doppler. So what it does is it creates something called a beat phase, and it can model that and extract the original signal from that. Your receiver's doing this, and how long does it take it to do this? 10 seconds? 15 seconds? To me, that's amazing, and you can be walking while it's doing it. All right. So that's if there was nothing affecting the signal. But there's things affecting the signal as it comes through the atmosphere, the ionosphere, the troposphere, not to mention multipath and the other stuff. So you have to take into account those things too. The ionosphere is the area of the atmosphere where there's a bunch of charged particles bouncing around. There's oxygen and nitrogen molecules up there, and the solar winds come in and they knock the electrons out of the atom. So as the oxygen molecule said to the nitrogen molecule, I'm being bombarded by solar wind and I'm losing electrons. And the nitrogen molecule said, are you sure? And the oxygen molecule said, I'm positive. So that's what's happening. You've got a bunch of charged particles up there bouncing around, and it affects the signal. Now the thing is, it affects the frequencies differently. The faster, the higher the frequency, the less it's affected. So dual frequency receivers can model that. All right? Multi-frequency receivers can model that. So it can eliminate the first order of that error, which is, whoops, sorry, there it is. So it's, 4 meters or so. It can eliminate that part of it. And what's happening now is something we should be aware of. We're going through a cycle of sunspots that reflect the solar geomagnetic and other storms that are erupting in the sun. Very active now. Every 11 years, it goes through a cycle. And you can see this started in 1700. I'm not sure who did it in 1700, but anyway, 11 years it has a peak and then a trough, peak and a trough. Peak meaning the higher sunspot activity. It's good to know this now because we're in a very active part. 2013 may be around the peak of it, all right, but it's still active now. I'll show you what it can do. At the Space Weather Prediction Center, you can look at all this information. If you have trouble getting to sleep at night, you visit that site and no, they have a lot of good information. So it could do these three things. It could knock out your communication, first of all right, whether it's cell or UHF radio. It could knock out your communication, which means you're out of luck, right, for real time. It could also charge the satellites themselves, create surface charging on the satellite. Well, what does that do? It messes up the electronics of the satellite. It affects the signal coming out. It could affect the orbit of the satellite, which is what you're using to figure out where you are. And it can add noise to your result. You'll see your RMS go up and your precisions go down, up. You'll see the precisions be less and less and less. There'll be higher numbers. So it could happen for 10 minutes. It could happen for 3 hours. It's very variable, and there's no easy way to tell you. Just know that if you're having trouble initializing, okay, or getting communication, be aware of this, which means you should be thinking about planning a little bit before you go out in the field. What all this means is this. The last time we had a high ionospheric disturbance was 2000-2002, introduced almost 14 centimeters in air into your solution. In the low areas back in the mid-90s, it was only a couple centimeters. And a network will, at 30 kilometers, will still only be a couple centimeters, even with the high ionosphere, as compared to 10 kilometers back at those other ones. So there's an advantage for a real-time network because you're modeling the errors. This is the page, the Space Weather Prediction Center. This is a warning you can get. Very simply said, well, I'm getting ahead of myself a little bit, but there's a set of guidelines, real-time single-base guidelines. And they have the parameters in there. You can read them. It's available online. But basically, they can send you a warning. Here's a warning from March this year. And it says a K-index of 7 or greater anticipated. And it says areas of impact primarily north, okay, but voltage irregularities, surface charging, intermittent navigation, high frequency radio may be intermittent. These are some of the things that can happen. All right, so this is an event that happened in March, and they're still happening. The K7 level is on a NOAA scale of G3. Anyway, here's another picture. K7 is here, and here's the red there that shows it. So just some more things you can look at the site. Here's the NOAA scales, if you will, the Space Weather Prediction Center. The recommendation is if you get something like this, maybe think about if you really want to do real time at that time, because you may have effects that knock out your communication or give you problems. And this corresponds to a K7. So that's one. That's a geomagnetic storm. There's also solar radiation storms and radio blackouts. All three of them have parameters that you can get a warning sent to you if you just say, send me this when this happens. And they can get it within about 15 minutes of the event right now, which is pretty good. And they can tell when an eruption has happened on the sun too. If there's a big flare or geomagnetic storm blast from the sun, if they figure, of course the Earth is rotating, so they don't know where it's going to hit by the time it gets here. But if it hits us head on, you won't be doing real time. This is just to say, this is the ionosphere again. You can model that using dual frequency receivers. If you have a single frequency receiver, you can do real-time positioning, but there's a lot of hoopla you got to go through to initialize. It's not as robust. You can't go as far. You need antenna swap. You have to initialize on a known point. You can't do on-the-fly resolution. So, hey, use a dual frequency receiver. Also, in disturbance times like these, single frequency will not be able to mitigate it. The network can, but you need dual frequency anyway. Now, the weather part of the atmosphere, known as the troposphere, the theory has always been this. With single base, don't go more than 10 kilometers. That's the magic number for single base. Because this is the theory. When you're in single base positioning, you want the same conditions at the base as at the rover. Because you set your base up here, and you type in the coordinate and everything, and then you take your rover 4 miles away. Well, your base is sending corrections to the rover based on its coordinates and what it's receiving from the satellites. It's saying, okay, I should be getting this distance. Oh, I'm not. Okay, all right, well, I got to have this correction for that satellite, and L1 and L2, and this satellite and this, and it sends that to the rover 4 miles away. Well, if there's a storm front going over your base, and you're out in the sunshine here, your corrections are bogus, right? So the theory is you stay close enough to the base, then you get this, you're in the same conditions. And that's the guideline. Guideline is to always do single base when you have the same conditions at the base and rover. Real-time network mitigates the conditions around it, so it interpolates to a position where you are. Now, you could be 35 miles away or 35 kilometers away from that station. So there's a lot of room in there for some play, right? But it does a good job. So that's the theory behind single base. And the last parameter is orbits of the satellites. The satellites send down an almanac that tells the receiver roughly where all the satellites are to go look for them. Then it sends down an ephemeris of each satellite individually for as good as it knows where it is. But because you're doing real-time positioning, that orbit is only estimated. So it could be a couple meters off from where that satellite is. Now, does that affect you? Not too much. Not too much. If the guideline for static is don't use that. Wait till you get that precise orbit, which is the green line, smoothed to the blue line. And then you can use that, because you can see that affects your height more than anything, doesn't it? Remember, at the speed of light, a billionth of a second is a foot. So we get broadcast orbit information for real time. But it's okay. In a small project, works fine. But if you want precise heights, you're doing static, use the precise orbits that come out 10 or 14 days later. There's also rapid orbits that are almost just as good now. And you only have to wait, what, a day for them. All right, so all these errors combine. If you're doing single base, real-time positioning, those errors are distance dependent. They're saying they're dependent to the base. So you combine the orbits, the troposphere, ionospheric error, you end up with about 4 centimeters and 10 kilometers at 95% confidence. That would meet manufacturer spec. Is it better than that? Usually. But that, I'm just saying, that meets spec. Now, here's some of the statements from the manufacturers. Here's Trimble. Real-time kinematic surveying, horizontal 8 millimeters plus 1 part per million, okay, which is a centimeter and 10 kilometers. Vertical 15 millimeters, or a centimeter and a half, plus 1 part per million. That's that part per million that is reliant on the further away you go from the base, the better chance there are that you're in a different condition. Okay, so that's what they say. Now, you're saying, well, it's not so bad. You know, it's 2 centimeters and 10 kilometers. You know, that's not bad. That's 1 sigma, 65% confidence. Usually we work in 95% confidence. That means you got to double that. Okay, so you're looking at 3 centimeters, 4 centimeters, and 10 kilometers for verticals using real time. Okay, just saying. A lot of times we're better than that, and that's ellipsoid height. Then add the geoid model to it, you've got another centimeter, at least. All right, so that's Trimble. But they say network. This is the only one that does that. They say network RTK, the horizontal is only a half part per million. Really, I would say it was less than that, but that's what they're saying. And they say vertical is still a half part per million. and 15 millimeters, okay, at 1 sigma. I would agree with that for the vertical. The part per million, I would like to see how they got that. Okay, TopCon, real time is 1 centimeter and 1 part per million. Vertical is 2 centimeters plus 1 part per million. That's usually what you see. Again, that's 65% confidence. Ashtec is similar. Leica is similar. So all the manufacturers are saying, essentially, in 10 kilometers, you have 2 centimeters error at 1 sigma, 65% confidence for horizontal, and 3 centimeters for vertical in 10 kilometers. Okay? Now, precision and accuracy. Precision is your quality of alignment to what is the truth that you're using. All right? If you're using a single base, precision is how good are you relative to that base. If you're using a network like GolfNet, how good are you relative to that network of stations? That's precision. Accuracy is how that station aligns to the truth. If that's the truth, precision is the same as accuracy. If you're using a network, it's how the network aligns to, if your truth is the national datum, how that network aligns to the National Spatial Reference System. That's truth. That's accuracy. Precision is how you align to the network. And there's a difference. So, there we go again. So like if you look at your data collector and you have a 2 centimeter RMS. Okay. 2 centimeter RMS. So you have a spread. You have a spread, don't you? But the average of them that say your receiver is going to use is pretty good in that first example. So your accuracy is pretty good. Your precision's not so hot, is it? Second one, you typed in the wrong coordinate for the base station. Precision is great, but the accuracy sucks. Excuse my language. And then the last one, you have both accuracy and precision. Okay? So that's the difference. Real-time network has to be very precise internally. Very precise. If it's not precise coordinate-wise, that error will be slopped into the atmospheric modeling and give you a worse result for your rover. So the coordinates, and Randy, if you're still here, correct me if I'm speaking wrong, but your coordinates have to be very precise internally, millimeters, okay? And to do that, they have to be better than the National Cores network, because the National Cores network has a couple centimeters floating around in it. It's a national network. There's 1,800 and some core stations. So you can weight the cores when you do an adjustment, but your network has to be more precise than the cores network. Okay, so it's very precise. Hopefully, what we would like to see is that network is going to be aligned to the cores network to a couple centimeters. That would be great if everybody did that. And Randy has done that. So, now, the advantage of a network, we mentioned some of these things. For a single base, you need this stuff, right? If you're going to set up your base station, you need your fixed height tripod, your antenna, and your battery for your base station, and your battery for your radio, and your antenna tripod, and you need all the cabling and everything. Maybe you have to sandbag the legs, but, you have to have a secure site. You have to find the point too, don't you? Sometimes that's not easy. And then you have your rover. With the network, you only need the rover, of course. You need, I'll use the same name. Apologies to anybody with the name. But you need Fred. Fred has to be at the base station to guard it, to keep it from getting stolen. And he's kind of being wasted, isn't he? So, yeah, another war story. Private sector, we did some real-time survey, and we had Fred set up over, he was a young guy, and he'd been out partying the night before. And he was at the base station asleep. And we went out and did the surveying, and we drove by and we saw he was asleep. So we pulled over and we took all the equipment, put it in the truck and rode off and went to the park and ride. And we called him, yeah, Fred, yeah, we're done now, coming back. Huh? Okay. Oh, jeez! You know, so brought him a change underwear. And but you know, Fred is superfluous with a real-time network. You can double your production by giving Fred a rover pole, right? Or you can half your equipment costs by just using one rover and let Fred do something else. You know, so take your choice, but it's a very dollar-efficient way to survey. So also, that part per million error that we saw goes away, basically. That first order part per million error. So now you don't have any distance-dependent error because, let me see if I can get to this. Let's go right here. Because you've got stations surrounding you that you can interpolate error conditions to you. You're not relying on a point 5 miles back there. You've got a point over here and behind you. So what that network does, and these are just two examples of a network, it creates a cell of stations around where you are, let's say 6 stations. You have two-way communication. So you have anemia message sent back to the server. The server says, I see where you are, pick 6 stations around you, does a epoch ambiguity resolution of those stations at a certain epoch of time. Then, depending on the network, the next thing that happens is this. In GolfNet, most of the time, Randy, is it always VRS? Or do you have MAC2 or? Okay, so in GolfNet is this situation where the server sees where you are, says, okay, I see where you are. I'm going to create a virtual station. If this is where your rover pole is, it says, okay, I got your location. That's going to be a couple of meters, right? So it's going to create a station right here, as if it was a base station. And it's going to send you that information, so that now you've got a baseline 1.5 feet away. So there's no part per million error there. It's too close to have a part per million error. Then you go ahead and do your survey, and based on the corrections right here, that's virtual reference station network. Okay. Now, how far can you go from this virtual station? It's up to Randy. You can go 5 feet, 1 kilometer, 5 kilometers. Randy says 1 kilometer. So Randy will let you walk away from this virtual station 1 kilometer, then you got to establish another virtual station. And I don't know how long it takes to do that, 30 seconds maybe? Yeah, less than 30 seconds, you know. So that's a VRS network. Trimble does it, Topcon does it. A lot of the networks will do multiple mount points and multiple solutions. So this other one is typically what you might see with Leica. That's called, well, it has different nomenclature. Let's call it a master auxiliary. And it does the same thing, only instead of creating the virtual, I got them mixed up, sorry. This was the VRS, I'm sorry. Okay, there's your virtual station by the rover. I apologize. And this is the MAC network. MAC network does the same thing, only it creates a baseline from the nearest reference station. You say, well, wait a minute now. That could be 30 kilometers away. That's a lot of part per million then back in the, no, because it interprets the errors and sends them to the rover. The rover does the result. Okay, it does the solution. It interpolates the conditions for where it is. So the difference between the two networks, the server does the interpolation in VRS, the rover does the interpolation in master auxiliary. Which one's better? They're both fine. Both good. Okay? So you have a user ID, a password, a mount point, which means do I want CMR plus data? Do I want RTCM data? Do I want, you know, RTCM 2.3, 3.0? So whatever your rover would use. Other kinds of networks, reverse processing, let's not get too much into that. You just send the information into the system computes the coordinate and sends it back to you. And then what you'll see some places, like this example in Texas, is what they call a network. They call this a network of stations. And it is. There is a server for those stations. But there's no network solution. So it means that you're connecting to the closest station. Okay? So it means you have part per million error. There's no interpolation of the errors. Okay? Still a network, but it's a single base. Okay, that's just the message you're sending back to the server. Anemia GGA message, basically just your long autonomous position. Here's GolfNet, about 60 stations, right, Randy? 66 stations, excellent. And What can you expect from GolfNet? Well, that's a good question. I can speak generally. Across the country, which, if you don't mind me backing up a second, I'm sorry. There's about 107 of these guys across the country, more or less. Okay, the solid blue ones are public networks. The striped blue ones are public and private, and just the red is private. It's hard to see in this color, I know. Anyway, 107 of them, all different kinds and shapes: academic, private, public. The public networks are going to stop the state line, more or less. Okay, but there's private networks, like for instance where I am, it covers 12 states from Virginia to Maine. So interesting stuff, and they're sharing data, which is, to me, it's wonderful. The public networks will share data with the private networks. It's interesting, in order to get a license. Okay. So, generally speaking, across the country, a real-time network will give you a really good horizontal position. Okay, survey grade. The problem has always been orthometric heights or elevations. There's a lot of reasons for that. But one reason is you're using a model for the geoid that has errors. You're using benchmarks that have been established when and have moved or not as good. You're using your ellipsoid heights that have error in it. Whatever the reason may be. Most people have the luxury of having benchmarks they can trust around their work. And if by having that, you can do a localization to those marks in the ground. Maybe not so here. So therein lies the rub. What is truth? You know, you can use a real-time network for an elevation, but that's usually the highest error you're going to get from real-time network is that elevation. It may vary even, and it depends on the interpolation of the errors, the quality of whether you have multipath or not, et cetera, et cetera. There's a lot of things that go into that, and we saw how tough it was to get an elevation anyway, right, with GPS. So, if you can localize to a mark in the ground, or at least 2 marks in the ground, then you can get really good results from a real-time network. If you can't, you have to be able to live with 5 centimeters. Anybody have a reference about that that they've used GolfNet for? I don't know. Just that's my estimate. Hello? There we go. So the administrator has to, this is what Randy has to go through. All this stuff. Where does he get the money to do all this? You know, with the communication. Real-time positioning is all about communication, especially with a real-time network. Coordinates are less hard to establish than the communication. And one of the toughest thing now is the spacing. And this is from Gavin Schrock, actually, in Washington State Reference Network. But if you had a 120 square mile area, 200 kilometer area, square, and you had to establish a real-time network, it wasn't too long ago that you would space those stations about, oh, come on now, about 30 kilometers apart. If you did that, you'd need about 46 stations. Well, now things are expanding. Software's better, the firmware's better, the modeling's better. A lot of people are now at 70 kilometer spacing. The difference is you only need 14 stations for that. So 32 stations less than you needed 10 years ago. And that's a lot of money, millions of dollars probably. So that's the tough thing. How far apart do I space those stations? Those stations have to model error conditions for where you are. So if you're 30 kilometers apart, that means you're 15 kilometers from the nearest station, right? That's, you know, not real far. It's almost single base kind of stuff. If you're 70 kilometers now, you've got 35 kilometers to the nearest station. So you're modeling over that distance. So therein lies the rub. Okay, so the user, of course, wants to know how good his or her result is. What's my accuracy? What's my precision? Does it jive with Opus? Wherever Steve is. What is the network using? There's Steve. So there's a lot of variation, less than there used to be, believe me. But there's a lot of variation with what the network is using. What does your network use? NAT83. Oh, okay. So what adjustment of NAT83? Well, it probably uses 2007. Are you sure? You sure it doesn't use 2011 or Cores 96 or HARN or whatever? So there's all these different adjustments of NAT83. All right, it uses 2007. Okay. What epoch of 2007? What do you mean, what epoch? I said, well, does it use 2007.00 January 1st, or does it use as it was last week? Or what does it use? So you need a datum, an adjustment, and an epoch. You should need to know that. You need to know what you're using in the field, right? So most of that is published, but it's good to know. It's also good to know that it's not going to be the same as OPUS solution. I don't know how much it's going to vary. This latest adjustment of NAT83 2011, should give you, which OPUS is using now, okay, and using Geoid 12 now, by the way, should give you good comparison to a network using the same thing. Okay? Should. What we'd like to see is everybody can use whatever equipment they have in a network. We'd like to see a lot of people using RTCM data because that's generic and open. And there's a lot of message types that are being worked on just for real-time networks. Okay? So we'd like to see that. We'd like to see the network aligned to the National Spatial Reference System. We can't force anybody to do anything, but we'd like to see that. The National Spatial Reference System is these things, but basically we think of it as coordinates, right, for our points. And the basis. This is some of the RTCM 3.0 message types. This is just some of them. But you can see on this next page, it has something called state space error models, or error messages. What that simply means is, instead of saying, like your base station used to say, here's the correction for this satellite. Instead of saying that, which they call observation space, now it says, here's the correction for the ionosphere for this satellite. Here's the correction for the troposphere from this satellite. Here's the orbit correction. You see how they're drilling down now and getting more precise with the error messages. So that's RTCM data. Open, generic, freely available for servers and for rovers. We like that. And this is what I was talking about before in 10 years from now. Marks in the ground, antennas in the air, right? We've got a new datum, and here's our core stations, the blue circles. They're truth. Everybody repeat, cores of the truth. Cores. Very good. So they are truth. They're truth now. But we want to say, all right, I want to bring an elevation to my project, and I know the cores of the truth, and I know I should be able to use that with the geoid model and get a 2-centimeter accuracy to the national datum. Trouble is, we don't broadcast the data. So you can't do it in real time. Well, what am I going to do? You go to the real-time network, right? You go to GolfNet. As long as GolfNet is aligned to the truth, then you're going to get the truth. And that's what we'd like to see. So your marks in the ground are now secondary. You can use them, but we're not going to support them. They're not truth anymore to us. Truth is the core's antennas. Antennas in the air now are truth. So you're going to establish project control anyway, right? So you can do that. And you have to decide what benchmarks to use and blah, blah, blah. But a lot of people will be using real-time networks in the next 15 years for sure. Concern is, you can see the different kinds of networks here. The concern is if you work on a border between two networks, do you get the same answer using each one? Well, if they're aligned to the National Spatial Reference System to a couple centimeters, you will. That's what we'd like to see. Otherwise, you're asking for trouble. And believe me, things have changed. In Maryland, there were 4 real-time networks, all private. 2 Topcon, 1 Leica, 1 Trimble. Somebody went out, a good friend of mine went out probably 6 years ago now, something like that, 5 years ago, about 5 years ago. And he used all 4 networks. and he took NGS data sheets with him, and he occupied a couple marks around the state. And you know, some of them he'd have 200s and horizontally and 300s vertically, and then he'd hit another one, he'd have 400s horizontally and 8 feet vertically. And then he'd hit another one, and he'd have 20 feet horizontally and 10 feet vertically. And he'd hit another one, and have 200s horizontal and 300s vertical. So they were all over the place. So that's dangerous. Believe me, that's dangerous. We do have subsidence in the Chesapeake Bay, not as bad as here, of course, but the marks on our eastern shore have changed 0.2 of a foot. So if you use a data sheet for those marks, you're starting out 0.2 wrong. But if you build something from them, they are the truth, right? They are the truth. So you're going to use them. Just to say, there's a disparity. Antennas in the air, marks in the ground. And you want the networks to be aligned to the National Spatial Reference System. How can we do that? All right, 2 ways. One is from the network administrator, and Randy is playing ball with us. I'll show you. Another way is to have something in the field you can check. So I'll have fiducial marks, but who's going to set them? I don't know. Have fiducial marks in the field inside of a real-time network. Let's say 20 kilometers apart, 12 miles apart, and do good GPS static on them. And if you have to, level them from benchmarks that you trust. Not easy, I know. But then you have a mark in the ground established at a certain time that you know is very good in relative to the National Spatial Reference System. Anybody can take their equipment there, plunk it on it, dial into the network, compare the result to the data sheet, and say, I'm doing okay. Fiducial marks. That's a great way to do it. Who's going to do it? I don't know. And then the second way is to have a tool that the network administrators can use, that we're building actually, and maybe using 30 hours of data. It says 48 there, but say 30 hours of data from the stations of a real-time network. Randy has done this. What he has done is taken all those, well, not all of them, he's working on it, but he's taken a lot of the stations and submitted them to the NGS as Opus DB, Opus database stations. So what does that do? It puts them in a database at the NGS. It establishes coordinates on it based on his data in the National Spatial Reference System. Then what we do is we take his data and compare it to the Opus DB data, and we just develop a scatter plot. And there's the difference between the National Spatial Reference System and what Randy tells everybody to use. And what we like to see is like a 2-centimeter grid there. That'd be nice. So that's a tool that the administrators can do. And that would be, you know, it'd be something that'd be it would be promoted, but we can't make anybody do that. We're just hoping that people like Randy will say, hey, look, we've been, you know, verified by the NGS as of this date, you know, and have the little NGS logo there and stuff. And people say, oh, okay, Randy, you know. So we're hoping that by peer pressure anyway, we get some people to play. A lot easier for the public people than the private.